So my name is Filipo Perotto. I am a postdoc student at the University of Toulouse in the south of France, and I am the first author of this paper. The question on the paper is how to integrate shared information into the sensorial mapping of connected and autonomous vehicles. So it's a position paper. We don't have conclusive results yet, but I would like to present you the research context, a brief overview on the state of the art on self-driving cars, and in our specific problem of integrating the information shared by other vehicles, then explain you in some detail the problem and the approach we are proposing. This work is part of a project called Connected Cars and Human Acceptability. It's financed by the Regional Council of Occitanie. It's the region on the south of France. There are 4 universities inside. And we have a driving simulation platform like this one shown in the slide. And we can simulate different road situations, including self-driving cars. And it is also possible to introduce a human in the loop and eventually evaluate a scenario in terms of human feelings like fear, security, or comfort. In summary, to make a long story short, the idea within the paper is the following. To be able to drive by itself, a self-driving car must detect the objects around it. It is done basically by analyzing the data coming from the sensors. The vehicle must pay special attention to the dynamic objects into the scene, like the other cars and pedestrians. And when 2 or more self-driving cars are geographically close, sharing the same road situation, they can communicate to each other their list of detected objects. For example, in this picture, on the left, the blue car is receiving from an orange car this kind of message and is integrating the information in its own map of the scene, which can be seen in the picture at the right. But doing so is not that simple. The perception of my neighbor may be different from the mine. I need to solve the conflicts generated by possible inconsistencies, and to do so, I must consider the credibility of the source and the information reliability. Concerning connected and autonomous vehicles, as you probably know, we are talking about a billionaire global market, which is increasing exponentially year after year. It involves almost all the giants of automotive industry and information technology. We are watching today a big research effort on a scale perhaps never seen before for something where AI is so central. This kind of technology, beyond the fact of being a wonderful challenge for applied AI, is also a key concept for wondering with the future smart cities and new intelligent transportation systems. There is a potentially big social impact at stake. And maybe the most important motivation to work on this field is the true possibility of saving lives. Nowadays, car accidents kill more than 1 million people per year around the world. And the promise is that self-driving cars can help to reduce those warlike numbers. In the current state of the art, self-driving cars work thanks to the use of high-definition maps. The HD map helps the car to localize itself with centimeter precision. And it helps also to localize, to identify the road and the fixed objects in the scene where it is placed. It's much better than the GPS in terms of precision. And the HD map provides also a semantic layer to the vehicle with information like road signs, speed limits, stopping points, and so on. It makes easier this very hard task, which is self-driving. It works basically by fingerprint matching. It means comparing the data flow coming from the sensors and the 3D objects in the map. In this way, the vehicle is free to concentrate its effort in detecting the dynamic objects into the scene, like the other vehicles and persons. The other pillar of self-driving is having a powerful perception system. As you can imagine, to make correct decisions, the self-driving car must be able to observe and understand the scene into which it is immersed. It involves having robust and heterogeneous sensors. When we talk about external perception, it means cameras, radars, and lidars. This ocean of signals must be integrated with a powerful sensor fusion system and a lot of computer vision enhanced with machine learning to detect, track, and identify the surrounding objects. The last pillar in this state of the art is communication. A lot of investment and effort is being done to allow a vehicle to communicate with other vehicles, but also with road infrastructures or even the cloud. It uses the V2X architecture over Wi-Fi or 5G network. For our problem in particular, the most important fact is the possibility of exchanging messages to inform the localization of each vehicle and other properties like speed and direction and even intentions, and also messages allowing to share the detected objects. So in order to make a collaborative perception. As we see the problem, we can talk about a last phase in the process of sensor fusion. So once the in-vehicle sensor signals have been combined to create a high-level list of detected objects, the vehicle can listen to the other agents, the other vehicles or other structures that are communicating with me, and try to integrate their perceptions to complete or to improve my own perception. It means I can use the information given by the other agents to try to ameliorate, to improve my own perception. In this example, as you can see in the picture, a yellow car is approaching an intersection and its field of view is represented by the yellow region. A connected blue car, which is out of the yellow perception, is arriving in the other road. And this blue car can warn the yellow car about its presence, and it can communicate to the yellow car its position, speed, and direction. And beyond that, the blue car can also share with the yellow car its own detected objects. In this case, we can see that the blue car can see a motorcycle coming in the other direction, and it is out of sight of the yellow car. So the blue car can communicate the presence of the motorcycle to the yellow car. And all of this can complete the perception of the yellow car. So the example corresponds to the simpler case where a source can help me to complete the blind parts of my field of view. In the figure, I cannot see the motorcycle because a truck is blocking my view. But the blue car that is in the same scene, this blue car can see the motorcycle and can share this information with me. The remaining question is, can I trust the blue car? And what kind of decision I can take based on information communicated by third parties? This is a more complicated case in the picture. Several sources are detecting the same object, but with differences or inconsistencies or incoherences. For example, in the example, the blue car is detecting the pedestrian, and the yellow car and the road camera are also communicating the presence of a pedestrian more or less in the same place. In this case, I need to take into account, or the blue car needs to take into account, the confidence in its own estimates, the credibility of the other sources, and the reliability of the information they are sending. And it makes take all these properties into account before deciding how to integrate all this information together. So our proposition is to estimate the credibility of a source and the reliability of each piece of information based on 4 different functions. To evaluate the credibility of someone talking to me, I can consider its public reputation. So this is a particular function. In general, it's something more or less social. Given in the case of self-driving cars, it must be given by recognized road authorities. So it's the reputation of a vehicle, for example, maybe considering the mark or the year of fabrication. But I can also consider the trust I have on that source. And the trust is something particular. Is the trust, it's a feeling or an estimate I have of a given source. And I can construct this trust based on our recent and local exchanges. The other part is to evaluate the information itself and to evaluate the reliability of some fact shared with me. I can take into account the confidence that the source itself has on that information. And I can also estimate by myself the capacity of the source on having a precise information about a detected object, for example. And this last property or this last function we call reliance. In terms of representation, in the one side, I have my perception. When I say I'm taking the place of a self-driving car, I have my own perception with a description of my own field of view. I know the regions of the scene I can see and the regions I cannot see. I create a list of detected objects, each object with a set of properties like identification, position, direction, speed, acceleration, etc. And I have my own confidence on each of these estimates and each of these detected objects with these properties, with its corresponding properties. In the other side, I have a list of objects communicated by other agents. These agents can declare their own field of view, their own estimations, their own confidences, and I can associate with this information the reputation, trust, and reliance. So the credibility it is a function that analyzes a source. The credibility can be calculated by a combination of reputation and trust. For example, the worst value between trust and reputation. Reliability is a combination of credibility, reliance, and confidence. Trust that is used in the first formula, trust can be measured by using some inconsistency metric, like the Shapley value. It means analyzing how a given source is usually giving correct information or not, based on some facts I know that must be true. And finally, reliance, we suggest to calculate reliance as a function of the distance of a given source to the object the source is detecting, and the clearance, it means how clear is its field of view in the direction of the detected object. We see three different cases. First, when I cannot see a given region, so depending on how trustable and reliable the shared information is, I can either incorporate it as an extension of my own perception or just reduce the risk I am ready to take in the next maneuver. The second case is when I am confident on my own detection, but at the same time, some confident and contradictory information is coming from trusted sources. So in this case of conflict, I need to believe in my own perception, but I should reduce risk taking because I need to consider the possibility of being wrong. And the last case is when I have a perception or a poor perception of an object, maybe because I am too far or the object is partially hidden by some obstacle. And then reliable contradictory information shared with me can lead me to eventually correct my own perception. In conclusion, as you noticed, this is still a preliminary work. We are following the clues. There are open points to consider, such as the interdependency between these four functions: reputation, trust, confidence, and reliance. There are also other problems like deciding when to filter an information. It means what is the good threshold to consider that an information is not good enough. And the problem of deciding is the last figure, when to split or merge objects closely positioned by different trusted sources. It means two near close objects are the same, but with some estimation error considering the position, or there are in fact two different objects in the scene. Finally, I think the paper is a first approach to consider credibility and reliability when doing collaborative perception. Now, we must conclude a formal definition of the method. We need to evaluate and validate it using our simulator. And we hope that the discussion presented in the paper will help to shed light on that problem, which is still an open problem in the community. Thank you very much for your attention. I am ready for questions if you have some.